Okay. Hello, everyone. My name is Yousun, and a PhD candidate of the University of Texas at Austin. And I'm happy to present my research work today for today's session to everyone. So before getting started with presenting my research work, let me briefly introduce each background. Drill shaft footing is a structural member transmitting the force coming from column to the drill shafts driven into the ground. And generally, the drill shaft footing have the short shear span to depth ratio smaller than 2, and therefore recommended to be designed with the strut-and-tie method. And the configuration of the strut-and-tie model for the drill shaft footing determined by the internal force flow of the drill shaft footing. And it becomes complicated when the uniaxial flexural is applied through the column with the axial compression. So when the axial force is combined with uniaxial flexure to the drill shaft footing, the strut-and-tie model configuration looks like this figure. And this model contains the vertical column tie elements, and all the tie elements in the model should be fully anchored to the nodes to ensure full yield strength of the tie elements. And current provisions employing the extended nodal zone concept to define a critical section for the development of the tie elements. But this approach is only applicable to the singular nodes where the nodal geometry can be clearly defined. However, the vertical tie element in the right above the figure are connected with the similar nodes where the nodal geometry cannot be clearly defined. So there exists no clearly defined design recommendations for the anchorage checks for those tie elements today. And previous researchers proposed some column reinforcement anchorages in drill shaft footing designed with the strut-and-tie method. And among the proposals, the Williams and others proposing to use 90-degree hooks with hooks oriented outward to the column and extended down to upper layer of the bottom mat reinforcement. And this reinforcement detail is proposed based on the successful previous in practice footings, but all of these recommendations were not experimentally verified. Therefore, this study aimed to investigate the anchorage response of the column reinforcement through the large-scale testing, and a total of four drill shaft footing test specimens were designed and fabricated with 4 different anchorage details of the column reinforcement, straight, headed, and 2 hook bars with different hook orientations in opposite directions. And as I mentioned earlier, typically in practice drill shaft footing using the 90-degree hooks with hooks oriented outward to the column, but the orientation of the hook has been considered to play an essential role in its bearing action in structural elements such as beam column joint, as shown in the right upper figure. If the hook orientation of the drill shaft footing has to be considered by the internal force flow of the drill shaft footing, the hook orientation of the column reinforcement should be also oriented to inward to the column. So this study is aimed to investigate it with experimentally by comparing the test results of the 2 hooked column reinforcement specimens. And here's the test specimen dimension. Its dimension is about half scale of the rear side footing. And the test specimen include the bottom mat, top mat, and side face reinforcement to replicate the reinforcement detail of the rear side footing. And 4 of number 7 column reinforcing bars are used, and conservative amount of the bottom mat reinforcement was provided for the specimen to be governed by the column reinforcement yielding. And here's the test setup, and an eccentric loading is applied through the column cover to simulate the axial compression combined with the uniaxial flexural loading condition. And buried lateral restraint among the 4 supports can provide the stability to the specimen and make it possible to the specimen to lateral expansion. And here's the testing results and load deflection responses. And those three graphs are comparing the test specimens measured at three different load displacement measurement locations. The left one is measured the relative compressive displacement of the core, and the center one is comparing the tensile relative displacement of the core, and the right one is measuring the normalized center deflection of the footing. And as you can see, the load deflection curves of all the test specimens are comparable, but when we focus on the center plot, the green curve, the testing result of the inner-oriented column reinforcement specimen measuring the tensile relative displacement of the column cover. Its displacement did not increase a lot even after adding up all the column reinforcement. And the similar response can be observed in the footing displacement measure shown in the right plot of this slide. And also the research team dissected the test specimens orthogonally at the plane of the column reinforcement to investigate the inner force flow of the drill footing. And we identified three different types of the cracking in the drill footing. The first one is type 1 is observed near the top surface of the footing, and it's conical cracking from near the top surface because of the high strain level near the interface. And the second type, type 2, formed in the middle portion of the embedment length of the column reinforcement and caused by the strut AC shown in the right upper figure. And the last one, the cracking coming from the compression side of the column core to the bottom end of the column, looks like to be induced by the strut AB on the right above figure. And in the straight bar and headed bar specimen, all those three types of the cracking can be observed, but for the outer-oriented hook bar, the second type of the cracking is not observed, and the third type cracking is going underneath of the bend radius of the hook. And the inner-oriented hook bar cross section, we can observe the second type and third type cracking, but we cannot observe the first cracking induced by the high strain value near the interface of the column reinforcement. Also, the column reinforcement was instrumented with a series of the strain gauges to plot the stress profiles of the column reinforcement. When we compare the stress profiles of the column reinforcement, we can compare that, and we can identify that except for the outer-oriented hook bar specimen, the other specimens can develop a relatively high stress level near the bottom end of the column reinforcement. But for the outer-oriented hook bar, instead of the high stress level near the bottom end, it experienced a relatively high stress level near the footing to column interface. The research team also developed average bond stress profiles based on the stress profiles I presented earlier, and based on the stress values obtained from two consecutive strain gauges, we can compute the average bond stress level acting on the bar surface between two consecutive strain gauges based on this equation. And we also compare the estimated value to the analytical value specified in FIV model code. And as you see, the straight bar can resist the tension in the bar based on the bond stress only, and we can see the high bond stress level near the bottom end of the column reinforcement. And this high bond stress is induced by confining force induced by the diagonal strut in the right upper figure of the strut-and-tie model. However, for the headed bar and hook bar, we cannot see very high bond stress level near the bottom end of the column reinforcement, and it indicates that the tension in the bar near the bottom end of the column reinforcement is resisted by the bearing action of the head and hook. However, for the outer-oriented hook bar, it cannot activate its bearing action, so it resisted the tension in the bar solely based on the bond stress only. So we can see the bond stress distribution of the outer-oriented bar is going down rather than the other types of the anchorage types of the column reinforcement. So from the testing result, the research team could identify that all the column reinforcement anchorage could irradiate, but we can confirm that they are behave with the different anchorage responses. And also with the research team could identify that the diagonal strut flowing down to the drill shaft and the bottom end of column reinforcement induces a lot of high stress level of the bottom end of the column reinforcement. And this stress profile can be used to propose the critical section for the column reinforcement for the anchorage check for the column tie element in the three-dimensional strut-and-tie model in the future. And the proposal and the testing results are going to be published through the ACI journal paper within a few months. So I think the others can share the results together when the paper is going to be published. And also this project is also funded by the TechStat, and I'm happy to, this is all my presentation. And if you have any question, I'll sure do my best to answer them. Thank you.